Hello, this is Dr. Liu. In this video, I will derive the formula for refractive imaging. So let's take a look at the diagram. This diagram was a screenshot of my simulation. So this is that surface is a concave surface. This front side, you can ignore the front side. So there's no interaction here. There's no such interface. Only the concave surface is the surface. So we can see the object is on axis, the image also on axis. This is one particular ray that hits the interface here. So let's put N1 here and N2 as the two different indices of refraction. Assume N2 is greater than N1. So this blue ray that hits here, it would go along the dotted blue direction without that interface or medium, but it bends towards this direction because the N2 is slightly greater than N1, so it bends towards that direction. And that would be the backward extension of that green line, the dotted line that intercept with the horizontal axis here. So that one point there is our image. So it is a virtual image, as the ray never really originated. The green ray never originated from that point. The blue ray simply bends into the green ray. All right. So now to derive the formula, let's do some definitions. So these definitions are definitions of various angles. Okay. So first, let's define these angles here. So we can call this angle alpha, and we can call that angle alpha prime, one from the object, the other from the image. And we can call this angle, this is from the center of the curvature also to that point. So this is, let's call that phi. And the incident and refracted angle, we'll call that theta 1, theta 2. So the incident angle is between the incident ray and the normal. So this is the incident angle, theta 1, and the refracted angle is between the normal and the refracted ray, so this is theta 2. All right, so we have this relationship. So refractive index sine theta 1, the other index sine theta 2. Right, so that's law of refraction. Okay, so because we have small angles in general, the alpha prime, these angles, thetas, and also the phi angle, they're supposed to be small. I'm actually exaggerating it to make it easy for me to draw the diagram. So all angles are small. So if I have an angle alpha, let's call it beta, will be approximately equal to sine beta, also approximately equal to tangent beta. Okay, so we'll do that approximation, and we'll draw a line here from this arbitrary point down to this optical axis right here, and we can call this height h. So this is perpendicular. And we can define some distances, and let's see, the distance here between the center and this vertex, we can call that v. So that's distance r, and that's also distance r, by the way. So let's mark it there as well, distance r. And the distance between the eye, the image, and the vertex, you can call that image distance, but I'm going to use a different color. So this S prime, I'm using a different color because this is not necessarily a convention compatible. So let's also replace that with a different color. So it's not by convention that we have established before, or not necessarily by convention. So we'll do that as well. So that is the object distance from object to vertex, right? Okay, so now we have these definitions, we can start finding relationships based on the law of refraction. So first, let's use a small angle approximation. So now we have theta 1, and here we have theta 2. Okay, so if you look at this phi here, this angle, and you look at this this triangle with the blue solid and dash blue and this dash black, this whole triangle here. So this outside angle, we have phi, that is equal to the sum of this angle theta 1 and that angle alpha. So that's theta 1 plus alpha. And we can also look at this phi with this dotted green line and this section of the dash blue, this same section of the dash black. So we conclude that that is equal to this angle, slightly smaller than theta 1 plus that alpha prime. And this smaller angle is the same as that angle, the theta 2 refractive angle, because the green basically follows the solid into the dot. There's the same angle here. So that is equal to theta 2 plus alpha prime. Theta 2 plus alpha prime. So now we have an equation. We can equate that with this because they're both equal to phi, which is one way to do it. Or we can plug this into those equations and use that equation. Okay, so it's actually this equation. It actually doesn't really matter that much because we're using small angle approximation. The equations are all trivial. So why don't we just do this? Theta 1 is equal to phi minus alpha. Theta 2 is equal to phi minus alpha prime. Okay, I'm going to plug these into the law of refraction. So N1 phi minus alpha equals N2 phi minus alpha prime. All right, and because the angles are all small, all angles are small, we can use phi or sine or tangent phi for phi. So what is phi? This right here. So sine phi would be h over r. Tangent phi is h over this portion, but we can extend it all the way over here because we're using small angles. So either way, let me do this, because that r being a positive quantity is not by convention. The convention has this as a concave surface. Excuse me. Concave surface, so it should be a negative. So this being a positive quantity is not by convention. So let's say that in our drawing we have the blue quantities. So R, S, and S prime, they're all greater than 0. They're just segments, lengths of segments. So they're not by convention. And we're going to use those to replace the angles. All right, so now we have N1. So phi is, or sine phi is h over r. So h over r. And the alpha here, alpha would be h over that length, or h over this length, but we can replace this length with the whole length of s. So alpha will be h over s. We're slightly overcounting that distance, but we have small angle. So this is basically minus h over s. So minus h over s. Right. And the other side is N2 and times the same thing, h over r, and h over s prime, because this over that distance, almost the same as over that whole distance there, which is s prime. So I'm just going to copy that, because switching color, it's kind of time consuming. So here all I have to do is to put a prime here. So that's what I wanted. So phi minus that. And everything has an h, so we can divide out h, and we'll have, let's divide out h. So we'll have n1 over r, and we also have this n2 over r, so minus n2 over r. So let's position the r over here. So those are the two terms. And we have the n1 with a negative s. We'll put it on the other side. So that becomes n1 over positive s. And then we have the n2 over the s prime. So n2 over s prime is a negative. So here's s, here's s prime. Okay, so finally we're done with all these coloring. Okay, so now let's consider the convention. So these are not by convention. So let's use convention. And what is our convention here? Okay, so convention, by convention, the object distance is positive. It is if it's on the left side. So we have this s here, and it is compared to the s. And we also have s prime. This s prime is going to be a negative quantity. So let's do this. S is a positive quantity by convention. S prime is a negative quantity by convention. And the r, because we have a concave surface, we have a negative r. So that's how these are. And the blue ones are, well, only one of them is compatible or consistent with the convention, is the s. The other two will have to produce a negative sign when they're replaced. Okay, so now I got how this replacement is going to go. The r is going to have negative, so there's a negative, and here's another negative to get the negative into positive. And the s doesn't need to change. This s prime is negative, it needs to have a negative, so that. And I can rewrite it into n1 over s plus n2 over s prime equals n2 minus n1 1 over r. So this is the refractive imaging formula, and you can use this to find out problems of one surface in refraction or multiple surfaces, thick lens with two surfaces and a medium in between, or you can find thin lens formula all based on this one formula from refractive imaging. Thank you.